Okay, we're starting Unit 8 today, and hopefully you're feeling good about the test tomorrow. I know we're doing Unit 7 test tomorrow, and your meeting review book will be due tomorrow. And my plan is not really to talk about Unit 7 at all today. Just to start talking about Unit 8, and to start nice and easy. We're going to talk about area between curves, is what we're going to be doing today. And what else was I going to say? Your homework is on this website, which is you can click on the link on Edline, or you can. This paper shows you what to do, and I think we're good then. And it will be not checked until Monday. I knew I was going to say that. Is that what you're going to ask? Yeah. So feel free to not. No, Tuesday. President's Day. Okay. So our goal in this unit is to talk about some applications of integration. We've already seen plenty of applications of integration in lots of nice AP problems we've done, and snow removal problems, and whatever else, right? By the way, that snow removal AP problem couldn't have been more appropriate. Like I felt like I was doing an AP problem when I was like every 3 hours shoveling, and I was, remember that? I had like a snow removal function, which was like somewhat discontinuous, and then there was like this continuous snow accumulation function. I felt like it was a calculus problem to make it when during that big snowstorm recently. We're also going to do, in that picture you saw a solid of volume of revolution. We're going to do some of those. We're going to do some other exciting things too. All right, so the question that motivates today's discussion is how do you find the area between two curves? And it's actually something that I think maybe some of you have thought about already. Like we've already made you do some of those, kind of, a little bit. So we'll try and take a little bit deeper on the way. But in the end, this lesson will not like stretch you super far, I don't think, right? Like let's try to start nice and easy, okay? So one way to do this would be to split this into lots of different areas, like this comment on the slide suggests. Do you understand what we mean by that? And use addition or subtraction to kind of piece this together. I'd be like, okay, well I know how to find the area inside here, you know, right there using the area under this curve, and I know how to find the area under here. It would be the same, and I could like find the area under this and subtract from that, and then I could find this area. I could find, I don't know, what would I do? I'd find the area of from here to here maybe. You know, there are lots of ways you could like piece it together. That sounds like terrible. It sounds like a really bad idea. So the better idea, and some of you, like I said, have already thought this through maybe, is to consider the small strip, vertical strip, right? And we want to ask, what is the length of that strip? The length of that strip can be computed by doing what? Say it again. Subtraction of what to, of what? Yeah, if we're calling this y1 and this y2, you might say y1 minus y2, right? Okay, cool. So the length of that green strip is y1 minus y2. And the width of that strip is, if it's really a very thin strip, we might say the width is, what'd you say? Well, let's talk calculus though. We still want it to be small. Yeah, we want to call it dx. How about? And then our goal would be to add those all up, right? That's a rectangle. It all comes back to infinite sums, limits, Riemann sums. The name of the game. It's the only game in town. And so the length times width for any given one, no matter whether we're here or whether we're down here, we can compute the size of this little rectangle, this very thin rectangle, as being 2 minus x squared plus x times dx. And then we're in calculus class, so we have to throw an integral in front of that. And it's non-trivial maybe to even figure out also, let's just not just say like, okay, game over. There's actually a little bit of discussion around how to get these limits of integration too, right? Like you might even have to, if this was the question, and we'll say more about this as we move forward, you might also have to think, what are those x values? And I think you'd be able to find them without too much trouble. But I'm just saying it's not like an immediate write down, is it? You have to maybe do some thinking to realize that -1 and 2 are the correct limits of integration. Okay, so we'll actually solve this then too. But notice that this all assumed, this whole discussion rested on the assumption that the top and bottom functions were always the same. Like we always compute the volume, the area of that little rectangular strip in the exact same manner, no matter where we are between x equals -1 and x equals +2. It was always computed in the exact same way. Because that assumption will like be challenged as we move forward and do some other interesting ones. Yeah.
Is area here always positive?
Yeah. Why is that going to be the case here? Again, think about my assumption in bubble. We actually do mean area this time. Yeah, because y1 is always greater than y2, you'll always get a positive answer here, which is okay. So we're actually not being like we're not being. I mean, we used to use like area under the curve kind of real loosely, but we're not being loose here. Actually, we really do mean area. If you've done the setup correctly, you will get a positive answer. Yeah.
Where's around half of the class?
Say that one more time.
Like, where's around half of the class? Where's half of the
Oh,
class?
there's a meeting. I think there's some stuff happening, whatever that stuff might be.
So you're recording.
2 things maybe?
So that's why you're recording this.
I am recording it, yeah. Is that okay? You're on. Do you want to say hi, Mom?
Hi, Mom.
There you go. Okay. Okay, and then let's actually compute this integral. This is not the glamorous part of the problem, but we can do it. By the way, I stole some of this PowerPoint, pieces of it from the Sketches PowerPoint, and I'd like there to be parentheses around that. I'm not a fan of that. Okay. So you know how to anti-differentiate a polynomial, so yay. I'll just skate over the details here. You know how to plug stuff in and add fractions, and yay. I promise that in the end, you will get the area, the exact area between the curves. It's 9/2. Yay. You could also, by the way, if you had a calculator, sometimes you might not. You could init this function, right? And you could just skip all the work and say 4.5. So feel free to try that if you want to just confirm quickly, quick and dirty, that in fact that integral does come out to be 4.5. Any other questions so far? Jack.
So essentially the method, so what determining the line of y plus x equals
That's arbitrary. It doesn't matter. I mean, that's an example one. But every single, that's what I was saying is, no matter where we are, the size of this rectangular strip, this very, very thin rectangular strip, is computed in exactly the same way, and the answer is it's y1, that is 2 minus x squared, minus y2, that is negative x, times dx, no matter where we are, whether we're here or here, and that assumption matters actually, because what the top function is and the bottom function is, like, will be maybe something to have to think about. That's the other given in that problem. You're like, oh, this is easy. But if I just handed you those functions without the picture, you might actually have to think hard first, maybe, about what it even looks like and which one is the top and bottom one. You might have to plug in some, there's some more discussion there too if I just handed you the problem. I brought it to you nicely packaged already. So I don't know that you'll need to memorize that formula, right? It's not maybe even, you can feel free to write it down, but in general, it's just like top function minus bottom function kind of just makes geometric sense, doesn't it? Yeah.
And you also cover this with, I think, integral f1 minus integral f2.
Absolutely. Come at this from an algebraic perspective, but I will say the reason, in fact, the reason I mentioned that we've kind of discussed this before is because when we did that property, when we introduced that property, how do you prove that that property is true? The answer is the picture I just showed you, right? We actually go back to thinking about Riemann sums. It's rectangle minus other rectangle, and that's actually why it works. So I think you'd be begging the question to go the other way. This actually is what proves that property of integration, but we should remind you that you actually have done this before, though, actually. Yeah. You knew that you could do this. Combine two integrals. You don't have to do the integral from a to b of f1 minus the integral from a to b of f2. You can just do it this way, yeah. Okay, let's consider a second example. Here's a curve, and we're interested in finding the area of this region. If it's not clear which region we're talking about the region that you can't maybe see very closely, but there's a blue line right here. So we're looking at this region shaped like a wing, shaped like a shark fin. Yes, the shark fin region. Thank you, that's the word I was looking for. Shark fin. We're looking for the area of the shark fin. And I've got the whole picture in front of us. Okay, so the first thing you might try is because we just told you to try it, is try the same approach here. But of course, do you see the issue? I've highlighted them. Yeah, we have two different ways of computing. And by the way, this will work perfectly well. Do you see how I'm coming up with this calculation? You can do the integral from 0 to, and again, I'm skating over some of the details here. It's maybe it's not hard, but it's not immediately obvious that 0 to 2 and 2 to 4 are what we're integrating for. Integrating between. We're kind of skating over the pre-calculus details, which we assume kind of maybe you know how to find the points of intersection here and with the x-axis. Okay, with that assumption clear, is it clear how I came up with that set of two integrals? The first one represents the area just under the square root function. And by the way, does it work to say this function minus this function? I mean, we really do have a third function here, don't we? Y equals 0. So maybe we've always been doing this. We've just had the bottom function has always been y equals 0, right? Maybe we've always been doing this. Okay, so the point is we just split that, didn't we, into those two pieces. First integral gets this area. Second integral is like an area between curves problem like the last one, top minus bottom. Root x minus 2. Perfectly fine to do it that way. Let's just say that. But there is another approach which I think we'll find fruitful. Yeah, sorry, Elizabeth. Mm-hmm.
I just forget. You said this is
Correct. Yeah, and solve. Try it off to the side and see if you don't get x equals 2. I'm sorry, I wrote that wrong. 4, comma, something, 2. For both equations. In fact, I mean, it's pretty clear that they intersect there, because if you plug 4 into either equation, you get 2. Okay. Multiple boundaries means multiple integrals. But here's a way to come at this problem that I think you're gonna like. It's kind of fun. And there'll be problems soon where this is like really the way to go. So it's not like, even though I said the first way is a great way to do it too, eventually there will be some situations where this isn't really that optional. Plus, it's just good for you to like think abstractly enough to handle this. Are you ready? You like that strip? Do you already see this? This is gonna be nice. Why is this a good choice? Well, because this strip always has on its edges the same boundaries on the left and on the right, where that wasn't true up above. It's gonna be a little uncomfortable for you, like mentally, to be like, really? We're gonna go integrating up and down now? Yeah, we are. It's gonna be fun. Okay. So it's not a problem, though. I mean, we just have to do again top minus bottom. Yeah, top minus bottom. If we have to tilt our head, that's okay. Okay, we're gonna be like thinking about it this way. Tilt your head. Integrating this way. But if we're going to do top minus bottom and we're going to do everything with respect to y, then we better have two functions that are solved in terms of y2. This one's not hard. I mean, neither of them are hard, right? This we might call x equals y squared. And this we might call x equals y plus 2. So now we have these functions x of y. Ooh, is that okay for you? X of y are the functions. X is now being thought of as the dependent variable. Then when we subtract, this time we need to make sure again we're thinking about top and bottom, or right and left, I guess we're thinking. But the point is big things that have big x values minus things that have smaller x values so that it comes out positive again, right? So again, you could tilt your head this way and be like, oh yeah, top function, bottom function. But also keep in mind too, what we're trying to do, things that have bigger x values are the ones here. These points here have bigger x values, don't they? Then points along here. For any given y value. For any given y value, the x value that generated by this function, this x value will be bigger than this x value for any given y value that you might choose on the interval 0 to what? 0 to, where are we choosing y values from? Notice this interesting difference too. We're this time integrating from 0. We always like to think about integrating from low to high. So from 0 to 2 this time, right? Okay? it'd be worth actually doing the integral, splitting it up in the way we talked about with dx first, and doing it in this way and seeing that in fact we do get the same answer. Okay, so this will be our preferred method maybe as we go forward, especially as we encounter harder examples where the first way is maybe impossible. But this is just even looking at that might be uncomfortable in your mind. Oh, what? We're going to integrate with respect to y? Keep in mind that everything needs to be in terms of y. If you're going to make a strip horizontally, then the width of that strip is dy. The functions better be functions of y. Ugh, and that's a little uncomfortable. And the integration limits need to be in terms of y. Everything y. So, again, skating over the details, you get 10/3. Feel free to F-init that. And when you F-init this, by the way, you're welcome to enter this and when you F-init this on your calculator. Some of you have the new pretty one, right? The new pretty integral F-init. So you can enter it just exactly how it looks. But feel free. Remember y is just, once we go to actually algebraically thinking about this, y is just a dummy variable. So if you want to use F-init and you have x plus 2 minus x squared dx on your F-init, that would work fine. So F-init works just great with any letter. You can use your favorite letter, y is fine, for example. So give it a try and make sure you get 3.33333. Comments, questions on this crazy new approach? You like integrating with respect to y? Makes you happy. Makes me happy. Okay. So in general, here let's kind of like step back and say what we've done today. Sketch the curves. I think that's not like, you might be like, duh, or maybe you'd be like, I don't need to do that. I don't know which camp you're in. But I do suggest it for reasons that haven't become obvious today yet, because like I've given you all the pictures. That's maybe a mistake here. So don't worry, you'll have plenty of opportunities to think this through yourself. But it's important that you be able to sketch the curves. First of all, to make sure you understand like what things are on top or bottom. You might be in a situation where you need to make the choice, someone doesn't tell you, about which way you're integrating with respect to x and y. And making that choice will be helped by you having a picture. So that's part 2 as well, right? So once you have the picture, now you can decide on vertical or horizontal strips with more clarity. Pick whichever is easier. If one of them generates like 3 different integrals, that might have been like not a great choice, right? One of them might just knock it out quickly with one integral. And then write an expression for the area of the strip. Keep in mind which things we're trying to do here. If we're doing horizontal strips like we just did, then your expressions need to be all in terms of y. And your differential is dy. And your limits of integration on number 4 now are going to be in terms of dx, in terms of x or y, depending on which situation we're in. And then, of course, integrate to find the area. And, in the context of a calculator problem, and I'll say this about everything in this unit too. If you're given a calculator, a lot of times what we're interested in fact, we'll even ask you, AP will even ask you, as maybe you've seen some of this type already, they'll just say, write an expression with integrals. This is the non-calculator part. Give me the expression for the area in between these 2 curves. Go. But it's a non-calculator piece, and it's like, even if you tried to do it, it might be like really difficult, or impossible possibly. It might be functions that are so terrible that you just don't even know how to integrate it by hand. So the big point on this unit, like on the last problem, we have like maybe if it's a 5-point problem, the last problem, 4 of those points is wrapped up in me seeing your integral expression. Limits are correct, you got a dy, and everything is right. And then 1 point for the integral. Whereas like in previous units, we would have been like, well, we really want to make sure you know how to anti-differentiate and like add and subtract and combine fractions. We don't really care about that very much this time around, right? In fact, so much so that we might even say, don't even evaluate. I just want to see your setup. So make sure that's clear in your mind, that you know how to write the integral expression really nicely. Because that's where a lot of the points, not just in this lesson, but in a lot of the tasks we'll be encountering, that's where all the points are going to be wrapped up in this unit. We know you know how to integrate now. We don't have anything else to teach you about symbolically integrating, like you're experts. Okay, so now I have for you some practice beyond what you'll do tonight. The homework tonight you're completely and totally prepared for, I think, to give it a try. It's on that website. So give it a try. But I have a worksheet right now that I'm going to pass out, and I'd like us to give this a try. This will emphasize, I think, some calculator skills too, like I've just been talking about. So
Should we have the online number for tomorrow or for after?
yeah, it'll be due actually on Tuesday when we come back after President's Day. So you're welcome to do it tonight. You're fully equipped to do it, but I will not check it until Tuesday. I think everyone has this worksheet. So this is what we'd like to be working on right now. And then